Welcome back. In this segment, we'll address some basic concepts of video enhancement. Clearly, when we deal with videos, we can always treat each and every frame of the video independently and apply a two-dimensional enhancement or processing in general technique. However, in doing so, the temporal correlation of the video is ignored. Taking this correlation into account, one can typically obtain improved results. One of the ways for us to take this correlation into account is through the use of the motion in the video sequence. We describe in this segment some of the basic ideas in performing noise smoothing in a video sequence. We describe three-dimensional spatiotemporal filters which either ignore the motion or take the motion into account explicitly or take the motion into account implicitly. We know from last week that motion estimation is a challenging task. It's clearly exacerbated due to the presence of noise. Ideally, a preferred solution would be one which takes the motion estimation error into account when performing intensity estimation and the other way around. We'll also put some of these ideas to test with video animation from the movie Fantasia. Due to the process that was followed for filming animation early on, there is a plethora of artifacts in addition to noise, such as scratches and blotches and flickering. We demonstrate how some of these simple ideas can considerably improve the visual quality of the video. So, let us proceed with this exciting topic. First of all, any of the image enhancement techniques we covered so far can be applied to video if we process each frame independently. In many cases, the results will be satisfactory. However, with such an approach, the interframe correlations or the temporal correlations in a video are not taken into account. By considering such correlations, improved results can be typically obtained. In some other cases, a two-dimensional enhancement technique can be extended to 3D. We can, for example, consider a group of consecutive frames and perform histogram equalization in the resulting 3D volume of pixels. We will discuss some basic concepts for the problem of noise filtering. Again, we can filter each frame independently using a two-dimensional spatial filter, or we can look at each and every pixel over time and filter the resulting one-dimensional time signal. So if we look at a set of consecutive frames, frame k, k minus 1, k plus 1, k plus 2, I can consider the pixel at the same location, and then a time domain one-dimensional signal results this way. So both of these approaches, 2D spatial filtering or 1D temporal filtering, were tried first in filtering noise in video. We will discuss here three-dimensional spatiotemporal filters, which have as special cases 2D spatial and 1D temporal filters. Such filters can be classified into three groups: the ones that completely ignore motion, the ones which take motion into account implicitly, and the ones which take motion into account explicitly. As a specific case, we will look at an example from animation video. In addition to noise, other artifacts are present which need to be removed as well. Similar problems are encountered in processing digitized motion pictures in general. The degradation model, assuming additive noise, is shown here. So we want to operate on the observed video G, ijk, and obtain an estimate f hat of the original video f, ijk. In doing so, we can ignore the motion, take it into account implicitly, or explicitly estimate it as shown here. For estimating the motion, down here, the noisy blurred frames can be used, coming from this direction, but also the noise smoothed ones can be used, coming from the output here. So the past noise-smoothed frames can be used, and the current noisy frame can be used this way to estimate the motion which will be utilized by the intensity filter. A desired solution is if the estimation of the noise-smoothed intensity signal and motion are done simultaneously instead of sequentially or independently, by taking the motion estimation error into account when finding an estimate of the intensity values, and the other way around, by taking the error in estimating the intensity into account when estimating the motion. We show here the form of a three-dimensional finite impulse response FIR filter. A neighborhood S is defined, which can contain only past values of the current pixel, but also future values. Then the filtered value at location I, j, k is the weighted sum based on the weights provided by the values of the filter, the weights W, P, Q, L, of the pixel values in the neighborhood S. A prime example of this is the three-dimensional flat filter or the average filter. In this case, all pixels have equal weights W. Another example is the three-dimensional Wiener filter. We will be talking about the Wiener filter in week 7 for two-dimensional images. The main idea is that the weights will be defined based on the three-dimensional autocorrelation function of the video. We have also not talked about autocorrelation. We'll do so in week 7. With such approaches, the motion in the video is not taken into account. This clearly will result in smooth temporal edges. The motion can be indirectly taken into account by making the weights a function of the temporal activity or edges due to the moving objects. So, for example, after the temporal edges are detected, the pixels belonging to them are not considered by the FIR filter. Another class of non-motion compensated spatiotemporal filters are infinite impulse response IIR filters. They have the form shown here. The filtered value f hat is the convex combination of a prediction f hat of b, which is carried out based on processed values belonging to the past of the pixel being processed, and the noisy observation g. This convex combination is determined by the coefficient alpha. An example of a prediction is shown here. The important point is that this neighborhood S includes only past pixel values. That is, the filter structure allows recursive computation of the result. So if I consider here the current frame K and the previous frame K minus 1, consider the pixel here at location IJ. I'm interested in finding the filtered value of the pixel IJ here denoted by X. So if I consider this neighborhood for the current frame, and it can be this neighborhood for the previous frame, then this shaded region forms these two regions. The union of them forms the region S here, based on which the prediction will be carried out. And again, all the pixel values in these shaded regions have already been computed, and therefore this is a recursively computable structure. The three-dimensional Kalman filter has the form shown here, where specific expressions exist for the gain alpha. Another form of spatiotemporal filters are order statistic filters. We talked about them for two-dimensional signals during this week in an earlier segment. The expression for a multi-stage median filter is shown here. It consists of 4 unidirectional median filters, in the spatial domain and one along the temporal direction. So M1, 2, 3, 4 are the outputs of the unidirectional filters in the spatial domain, while M5 is the output of this unidirectional median in the temporal direction. So the final result here is the median of the maximum of these 5 outputs, the minimum of the 5 outputs, and the observation G. The FIR version of the motion compensated filter is shown here. The motion is now taken explicitly into account. One can use any of the techniques we covered last week in estimating the motion in carrying out this spatiotemporal filtering. So the region here, S, that tells us which pixels we should utilize to carry out this filtering operation, is not fixed, is not rigid like a parallelogram in the three-dimensional space, but it changes shape based on the motion parameters. So for example, if I consider here the current frame and the previous in time frame k minus 1, I'm interested in finding the filtered value at location ij, and if I consider the values p equals 0, q equals 0, and l equals 1, so I'm looking at the ij location, the previous frame. In finding this filtered value, I will not consider this pixel here, but instead its motion compensated version. So in the I direction, we will use the vector d hat x k minus 1. So this is the x component of the estimated motion vector, while in the y direction I'll use the estimated motion vector d hat y k minus 1. So the two of them will give us the compensated location of this pixel. So it is this pixel that will be multiplied by the weight 001 according to this, and will contribute towards the estimation of the pixel ij at the current frame. The IIR version of the motion compensated spatiotemporal filter is shown here. This expression is identical to the non-motion compensated IIR filter. However, the prediction now is done along the motion trajectories. So the neighborhood here is such that it allows recursive computability. Gamma are the weights, but again, I utilize the compensation in the x direction according to this vector, the y direction according to this vector, and therefore this neighborhood that I utilize to carry out the prediction is again changing according to the shape of the motion. We show here a specific application. We show a few frames from the Walt Disney animation Fantasia. A number of anomalies are observed in this short video. In addition to noise, flickering is present. Flickering is defined as this unnatural temporal fluctuation of intensity that does not originate from the original scene. You can also see on the upper left corner there a blotch or two blotches due to dust particles. In other parts of the video, there are scratches and fingerprints, and these all originate from the way that animation was filmed early on. So the animated scenes were painted onto clear sheets of polyester called cells, which then were placed on an animation stand and photographed 3 times, each time using a red, green, or blue filter. An innovation by Walt Disney produced the effect of dimensionality or depth by laying cells on top of one another and photographing them together. Each cell contained a different picture element, and the glass plate was then used to hold these cells in place. However, these plates often contained particles of dust or dirt, which was then captured onto the film. As already mentioned, different amounts of light intensity cause the flickering effect between frames, and also duplicated frames and severe illumination changes are often characteristics of animation film. So it is therefore highly desirable before the re-release of all movies, animation alike, to remove these artifacts and enhance the video. In dealing with the enhancement of motion pictures, we deal with a number of artifacts. The first one, as already mentioned, have the generic name of blotches, and they are due to dirt, sparkle, film abrasion, scratches, and fingerprints. There is also the intensity flicker, referred to also as bowling effects, as it was clearly demonstrated in the short animation video I just showed. And finally, there is another artifact due to the so-called vinegar syndrome. So for content that was stored on acetate-based film rolls, they progressively deteriorate, and these rolls can be affected by a number of artifacts, of film artifacts. One of the major problems of all film archives is this vinegar syndrome. The syndrome appears when, in the course of their chemical breakdown, the acetate-based film bases start to release acetic acid, which actually gives a characteristic vinegar smell. The vinegar syndrome has various appearances. It may show up as a partial loss of color, bright or dark tree-like branches, non-uniform blurred images, and so on. Some of the animation characteristics are mentioned here. The image sizes are large, so for Fantasia, for example, each frame is 2000 by 1200 pixels, and each color is 12 bits, therefore 36 bits per pixel. Due to that, we are interested clearly in simpler and computationally efficient algorithms. In animation, there is typically unnatural motion. The constraints the dynamics of natural objects are subjected to do not apply to animation, and we have arbitrarily large and complicated elastic motions taking place, and therefore when motion estimation is performed, additional care needs to be paid. We mentioned that these artifacts are present in older animation due to the way it was generated. This is not the case necessarily today, since animation is done digitally. And finally, there are the issue of duplicate frames, which might be due to frame up conversion and severe illumination changes. We outlined here a blotch detection algorithm that we utilize for the Fantasia animation movie. The assumption is that the blotches appear only in one frame. So the blotches are on the frame f of k, and an estimate of the frame f of k is obtained through g of k, which is clearly the average of the next and the previous frame to the f of k. Then the difference between the estimate g of k and the actual frame is found, and that's d1. So those regions with high d1 compared to the noise variance are classified as belonging to an artifact. However, moving edges will also be detected by this test. Therefore, more tests are needed to filter out, in some sense, these moving edges. By finding d2, the absolute difference between the previous and the next frame, the moving edges as well as the anomaly will be detected between these two frames. Similarly, by finding d3, the difference between the next and or the current and the next frame, edges and anomalies will be detected. Now, given these three different frames, d1, d2, d3, a binary mask indicating the presence of the anomaly is obtained in the following manner. For each of these differences, the mean mu and the variance sigma square are found, and based on these thresholds tau of I are estimated, which are based on this parameter int of I. Int of I is an integer and controls the number of pixels which are classified as an artifact. The higher its value, the fewer pixels will be classified as an anomaly. So once these thresholds have been found, a binary mask is obtained according to this formula. A pixel at a location mn is classified as an anomaly if b of I is equal to 1 for all three values, called b1, b2, and b3. So the inclusion of b2 and b3 effectively accounts for the presence of motion, because moving regions will show up in either b2 or b3, but not in both of them. So here's the frame of the Fantasia video. Here is the blotch or the artifact that we want to pull out, and according to the algorithm that I just described, here is the detected blotch for the three values of the parameter eta that is utilized to set the threshold based on which the binary mask is created. After the blotch is detected based on the algorithm I just described, then we utilize an algorithm to remove the blotch. The algorithm distinguishes between two cases, whether the blotch belongs to a moving area or a non-moving area. In the former case, a simple averaging along time utilizing the next and the previous frame is taking place, while if the blotch belongs to a moving area, then a motion compensated averaging is taking place, following the principles that we have covered already in this particular segment. So utilizing such a blotch removal algorithm, here is the result. Clearly the blotch here has completely disappeared and blended with the background. For the removal of noise for Fantasia, any of the filters that we covered in this segment can be utilized. A form of the filter is shown here. So the filtered value rather of the intensity at frame k at location mn is given by this expression. So this is the observed value, and this is the mean. It's a spatiotemporal mean which can be motion compensated or non-motion compensated. An important factor is alpha here, which is a function of a mask that can distinguish between moving regions and non-moving regions. Using some technique similar to the ones we used for the blotch detection, we can obtain a mask such as this one. So white shows moving pixels and black non-moving pixels. Actually, if a pixel is moving but is detected as non-moving, then ghosting so-called artifacts occur. So it's in many cases advantageous to increase this size of the mask. So this is an expanded mask. So for cases, for regions that there is no motion, alpha is set equal to 1. So in this case, clearly we perform some spatiotemporal smoothing here through this averaging operator, since the first term drops out. And for the regions that there is motion, alpha is set equal to 0, in which case we just rely on the actual observation. So here we show the enhanced version of Fantasia. It should be apparent that the flickering has been considerably reduced, and also the blotch that had appeared in the earlier version of the video is also completely removed. Let me show them now actually side by side so these differences are crystal clear. So here is a side-by-side comparison. Clearly some of the claims that were made can be substantiated. The flickering is reduced, the blotches are removed, noise is also filtered out. It should be clear by and large that the enhanced video is an improved version of the original one. This has been actually a quite successful project because also special attention was paid so that the resulting algorithms are computationally efficient. This brings us to the end of week 5. We learned quite a few things this week. We learned how to manipulate each and every pixel in an image independently from its neighbors. We defined a function or a mapping that will take the intensity of each pixel in the input image and map it into an enhanced intensity at the same location in the output image. This mapping can be linear or nonlinear. We define this mapping by looking at the image and assessing its quality. Of course, we can change the parameters that define the mapping or try a different mapping altogether until we are happy with the results. We also learned about the histogram manipulation approaches. In this case, our enhancement objective is defined in terms of the histogram of the image, a term that we defined in class. We desire our enhanced image to have a specific histogram. Such a requirement will then define the mapping we need to apply to each and every pixel in the input image. We also learned how we can reduce various types of noise in the image using both linear and nonlinear systems or techniques. If the linear system is also spatially invariant, then we have already learned how to describe and implement such systems both in the spatial and frequency domains back in weeks 2 and 3. We also learned how to make an image look sharp or how to decrease the dynamic range while increasing the local contrast. Finally, we saw that adding color to a black and white image can increase its appeal or help resolve some interesting questions in art applications. We dedicated the last segment on video enhancement. A considerable amount of the material we covered so far can be extended to 3 or higher dimensions. So even though we do not explicitly address video, implicitly we've covered quite a bit of material about it. Of course, now that we have covered motion estimation techniques in week 4, we are in a better position to address, for example, motion-compensated spatiotemporal filtering techniques. We also discussed a fun application, that of enhancing the animation video of Fantasia. Starting next week and for 2 weeks, we will focus on another fun topic, the cousin of enhancement, you might say, that of image and video recovery. So I'm looking forward to seeing you next week.